Now that you've made your prediction, let's check if you're right. Let's start by moving the north pole of the magnet towards the loop. You can see that as I push the magnet towards the loop moves away from the magnet. If I then pull the magnet away from the loop moves towards the magnet. So let's discuss why this is. If we've got a north pole here, then we've got magnetic field lines coming from the magnet going into the screen inside this loop. Now, as I push the magnet towards the loop, the strength of that magnetic field is going to increase. So we will have an increasing magnetic field into the screen. Now, Faraday's law tells us that the induced magnetic field is going to oppose that change. So we're going to have an induced magnetic field which is coming out of the screen. In order to get the magnetic field which is coming out of the screen, we must have a current which is flowing in an anti-clockwise direction around that loop. Now, as I move the north pole of the magnet away from the loop, I've got a decreasing magnetic field into the screen. So in this case, the induced magnetic field is going to oppose that change, so it's going to be a magnetic field which is also into the screen. So to get a magnetic field into the screen in this case, I need the current to flow around the loop in a clockwise direction. Now with the slit, let's have a look at what happens as I move the magnet towards and away from it. You can see in this case the loop does not move. So this is because we can't get a current flowing all the way around the loop, and so we're not getting an induced magnetic field in this case, and so there is no force on the loop as I move the magnet towards or away from the loop. So this is another example of Faraday's law, and this is one of my favorite demonstrations. So what we've got here is a solenoid. When I turn the power on, the current flowing through the solenoid is going to create a magnetic field. Now up the top here I have an iron core which is connected to an iron core in the middle of the solenoid. So when the solenoid creates a magnetic field, that magnetic flux is going to travel quite easily through this iron core, and so I'll get quite a strong magnetic field up here. Now if I place a metal ring onto that metal core, let's have a look at what happens when current starts to flow through the solenoid. Pretty cool, right? The ring jumps. Let's have another look at that. Okay, so let's explain what's happening here. So the solenoid is creating a magnetic field. Let's assume that the magnetic field it creates is traveling up the screen this way. Now, when I place the metal ring around the same iron core, there's a magnetic flux passing through the ring. And that magnetic flux, according to Faraday's law, is going to induce a current in the ring, which is going to create a magnetic field that opposes the applied magnetic field. So in this case, we have a current flowing around the ring, which should create a downwards magnetic field. So we've now got two opposite magnetic fields, the one traveling upwards from the solenoid and the one going downwards through this metal ring. So that gives us a repulsive force between these two magnets. Now, just to show that that's really what's happening, let's have a look at what happens when I place this ring with a slit down the middle over the iron core and push the button. you can see nothing happens in this case, because while the magnetic flux does cause some electrons to move, the electrons can't jump across the gap here, and so we don't get a consistent current flowing around the ring, inducing that magnetic field. So there's no repulsive force in this case. So let's have a look at a problem that we can solve using Faraday's law now. So the problem is a conducting bar moves on two frictionless parallel conducting rails through a uniform magnetic field of strength B directed into the screen. The bar has a mass m, length L, and an initial speed Vi to the right. A resistor with resistance R is connected in series with the bar. The resistance of the rails and bar are negligible. Part A, use Newton's laws to find an expression for the velocity of the bar as a function of time. And Part B, show that the same result is found using an energy approach. So in this case, we have a bar which is moving through a magnetic field. Now, as it moves, there's going to be a current induced in the bar, which can also flow through the resistor here. So let's start by working out what we can about that current. So we can use our right hand rule to see that the force on positive particles inside the bar is going to be upwards, or the force on the electrons, which is what actually happens, will be downwards. And so we're going to have a current which is induced around the bar like this. So we're told to use Newton's laws to find an expression for the velocity of the bar. So we know that the force acting upon this bar is going to be the magnetic force from this induced current reacting with the magnetic field here. So we can say that the force on the bar is going to be the magnetic force, and that will be given by I L cross B. Now, in this case, the current is flowing up the bar and the magnetic field is going into the screen. So these are perpendicular. So we can write this as I, and then this L is the length of the bar. So that's little l times B. So we've now got an expression for the force, only we don't know what I is. So to work out what I is, we're going to need to use Faraday's law. And Faraday's law tells us that the EMF, which is just the voltage, is equal to minus N d phi B dt. Now, in this case, we've only got the one loop. We've just got the one bar here. So N is going to be 1, and so this will be equal to minus d phi B. Now, in this case, phi B is the magnetic flux. So it's the number of field lines cutting through this region in here. And so this is going to be BA in this case, times dt, and A, that's the area of the loop. So if we let the distance of the bar from this part of the rod here be x, you can see that because the bar's moving, x is going to be a function of time. So we can write this as minus dB, and then the area is x times L dt. L and B are not changing with time, so we can write this as minus BL dx dt, but dx dt is just how fast it's moving, so this is equal to minus BLV. Now what we can do is use this to find the current, because this is just the voltage, and according to Ohm's law, the voltage is equal to IR, and so this tells us that the current I is going to be equal to minus BLV over R. So what we can do now is put this expression back into here, and we know that the force, the only force acting upon it is the magnetic force. I mean, the gravitational force will be balanced by the normal force from the rails. So we can say this is equal to MA. So we've got M, and let's put A as dV dt, is equal to I, which is minus BLV on R, times LB. So rearranging this, we've got M times dV dt is equal to minus B squared L squared V divided by R.
And we can rearrange this to write dv over v, putting all the velocity terms on one side, is equal to minus b squared L squared over Rm dt on the other side. So now we've got a differential equation to solve. So to solve that, let's integrate it. And we know that at time 0, it's got initial velocity vi, and we'll say at time t, it's got final velocity, which we'll just call v. So integrating this, then, we've got that on the right-hand side, this will just be b squared L squared on Rm times t, and the 0 will just be 0. So this will be minus b squared L squared over Rm t. And when we integrate dv on v, we're going to get log v. So this will be log v minus log vi, which using our log rules we can write as log v on vi. Now what we're trying to do is get an expression for v, so we can simplify this a little bit. If we raise each side, if we raise e to each of these sides, then we've got v over vi is equal to e to the minus b squared lt on Rm. And so this tells us that v is equal to vi times e to the minus b squared L. Sorry, I've dropped a squared off my L there. It was here and then I forgot to write it on this line. So b squared L squared t on Rm. So that's an expression for the velocity of the bar. So we should just make sure that it makes sense. As the time gets really, really large, we have this velocity decreasing, which is what we expect. It's going towards 0, because when we think about the current moving this way and the magnetic field going into the screen, with our right hand rule we can see that the force is going to be opposing this motion, so the force is going to be in this direction. So we do expect it to be slowing down in time, which is what we get. So now in the second part it says show that the same result is found using an energy approach. So let's start that here. We've got two types of energy involved in this question. The bar is changing its speed, so we've got a kinetic energy which is changing, and we've also got electrical energy because we've got a resistor here. Nothing else has resistance, but we do have a resistor here, and so electrical energy is going to be lost in the resistor. So we would expect electrical energy lost by resistor comes from the kinetic energy. So as an equation, the easiest way to think about it is the rate at which energy is used. So we expect that the rate of electrical energy used by the resistor is going to be the same as the rate at which kinetic energy is lost by the bar as it moves through the magnetic field. So electrical power, P, is equal to VI, or we can also write this as I squared R. And we've worked out what the current is up here using Faraday's law. So none of that was due to Newton's laws. So we'll end up with exactly the same expression for the current here. So we can write, well, the electrical power is going to be equal to B squared L squared V squared over R squared times R. So that's equal to B squared L squared V squared on R. Okay, and now what we'll need to do is work out the rate at which kinetic energy is changing. So P for the kinetic energy is going to be equal to the derivative of the kinetic energy, which is a half mv squared with respect to time, dt. And so when we differentiate this, the mass is not changing, it's just the velocity which changes as a function of time. So we've got a half m, that's constant, and then when we differentiate v squared, we get 2v dv dt. And so since p is equal to minus pk, we can say in this case we've got b, that's a b squared L squared v squared on r is going to be equal to minus, now let's cancel out that half with that 2. So we've got mv dv dt. And then again, we'll put all the functions of v on one side and dt and everything else on the other. So we've got b squared L squared on r, and then this m will need to come down here. And this will be equal to minus, this v squared here will cancel one of these v's here. So we'll end up with dv over v. So at this point, we've got exactly the same equation as we had up here. So solving it is going to be exactly the same. What we'll want to do is integrate it. And again, we're going from vi to v, and we're going from 0 to t. So when we integrate that, we solve it in exactly the same way. And so it is going to give us exactly the same expression. So we will end up with v is equal to vi e to the minus b squared L squared t on Rm.